So let's take a look at equations of lines and planes. So let's say I have a line, let's just label it L here, and then we have a vector V, and vector V is going to be parallel to the line L. And let's say L also intersects a point in the three-dimensional coordinate system. And let's go ahead and call the point 1, 2, 3. Now how could we find a vector equation that represents the line L? Well, the formula for the vector equation, R, is going to equal R sub naught plus the variable t times v. And so R sub naught is going to be a vector that represents the given point that is being intersected. So if 1, 2, 3 is going to be intersected here by the line L, well, the good thing about R sub naught is that its components are going to be the exact same as the intersecting point. So R sub naught is going to represent 1, 2, 3 in its component form. And so if we want to write it in its unit vector form in terms of ij and k, we can simply just write it as I plus 2j plus 3k. Now, vector equations and parametric equations are going to be similar because they both use variables in terms of t. So t is just going to be that variable, and then v is going to be the parallel vector. Now the general formula for R sub naught is just going to be in terms of its x component, so x sub naught, its y component, y sub naught, and its z component, z sub naught. And then the vector, the parallel vector v, is just going to be in terms of a, b, and c. So when we write the parametric equations are going to be in terms of x, or x in terms of t, y in terms of t, and since we're in the third dimension, z in terms of t. So x is simply just going to equal x sub naught plus a times t. So x sub naught is obviously, in this case, is going to be 1 if that intersecting point has the x component of 1. Y is going to equal y sub naught plus b times t. And z is going to equal z sub naught plus c times t. And so keep in mind that vector equations are usually written in terms of I, j, and k. So that's the way we'll put it in terms of our final answer. So for number 1, let's go ahead and find a vector equation and parametric equations for the line that goes through the point negative 2, 4, 10. So that's the intersecting point and parallel to the vector 3, negative 1, 3, and 1, negative 8. So that is going to be that parallel vector. So let's go ahead and label R sub naught right away. R sub naught is going to be the intersecting point but in component form. So simply it's going to be negative 2 as the x component, 4 as the y component, and 10 as the z component. And then the parallel vector v is just going to be, once again, 3, 1, negative 8. And so let's go ahead and write each of these vectors in terms of I, j, and k, or the unit vectors. So R sub naught in unit vector form is going to equal negative 2i plus 4j and then plus 10k. And then the parallel vector v in unit vector form is going to equal 3i plus 1j, or simply just j, and then minus 8k. So remember, the vector equation R is going to equal R sub naught plus t times v. So in this case, R is going to equal, if we plug in all the variables in, R sub naught, which is negative 2i plus 4j plus 10k, and then plus the variable t times vector v, which in unit vector form is going to be 3i plus j minus 8k. Now we can simplify if we want to, but this is also an acceptable answer for the vector equation. Now let's go ahead and find the parametric equation. So I'm going to go ahead and rewrite the vectors and its components for R sub naught and v. So R sub naught negative 2, 4, 10, and vector v, the parallel vector, is 3, 1, negative 8. So remember that R sub naught is going to be in terms of its components, x sub naught, y sub naught, and z sub naught. And v, vector v, is going to be in terms of its components a, b, and c. So once again, the parametric equations are going to be in terms of x, y, and z. And so x is going to equal x sub naught, which is negative 2, plus a, which is 3, times t. So then y is going to equal y sub naught, which is 4, plus a, which is 1, times t. So 1 times t is just t. And then z is going to equal z sub naught, which is 10, plus c, times t, so negative 8 times t. So I can just switch that to 10 minus 8t. And so those are going to be the parametric equations. So for number 2, we have to find a vector equation and parametric equations for the line that passes through the point 106 and is perpendicular to the plane x plus 3y plus z equals 5. So let's go ahead and start off with r0. So r0 is obviously going to be that intersecting point in its component form. So it's going to be 1, 0, 6. And if you want to write that in unit vector form, we can simply write it as r sub naught equals 1 times I, so just I, plus 0j, so that's out, and then plus 6k. So now remember, we need a vector that is parallel to the line, but in this case it gives us a plane. So let's go ahead and visualize for a second. I'm going to go ahead and draw a plane here. And let's say a line L is perpendicular to the plane. So it creates a 90-degree angle with it. So this means we need to find a vector that is parallel to L, but is also perpendicular to the plane as well. So this is going to be another vector here. Let's just go ahead and call this n, the normal vector, because a normal vector is going to be normal or perpendicular or orthogonal to the plane. Now planes are always written in the equation ax plus by plus cz equals some constant d, as shown here. And so a normal vector for a plane is always written in the form a, b, c. So the normal vector in this case, let's go ahead and write the plane's equation really quickly. So 1x plus 3y plus 1z equals 5. So notice it's in the form of ax plus by plus cz equals d. And so the normal vector for this plane is going to be equal to a, which is 1, comma b, which is 3, and then comma 1, which is c. So that is going to be the normal vector. And so if we put it in unit vector form, n is going to equal 1i plus 3j plus 1k. So once again, the vector equation formula, r is going to equal r sub naught plus t times v. Now we have r sub naught, and instead of v we have n, but they're basically the same thing because we have found a parallel vector for L. So rewriting the equation, we get the vector equation r is going to equal r sub naught, which is I plus 6k. So I plus 6k, and then plus t, the variable t, times the parallel vector, which is I plus 3j plus k. And so that is the vector equation. And so let's go ahead and find the parametric equations now. So we have r sub naught, which is labeled in terms of its components x sub naught, y sub naught, and z sub naught. And then we have the vector n, which is in terms of a, b, c. So once again, parametric equations in 3 dimensions are going to be in terms of x, y, and z, all in terms of t. And so x is going to equal x sub naught, which is 1, plus a times t, which is 1 times t, which is t. Y is going to equal y sub naught, which is 0, plus b times t, so 3t. So then that's just going to equal 3t. And then z is going to equal z sub naught, which is 6, plus c times t. 1 times t is just t. So those are going to be the parametric equations. Now, before I move on to the next set of questions, you might also be asked to find symmetric equations. And so all symmetric equations are is you take parametric equations and you eliminate the parameter, so you get rid of the variable t. And so what you're left with are those symmetric equations, and the formula is going to be like so. So we have x minus x naught over a, which equals y minus y naught over b, which equals z minus z naught over c. And so sometimes either a, b, or c could be 0. And if that happens, all you have to do is write it separately. So let's say a is going to be 0. Then we take x minus x naught, and we just rewrite it as x equals x naught instead. And that's going to be separate from y minus y naught over b equals z minus z naught over c. So let's go ahead and find the parametric and symmetric equations for the line that goes through the points 1, 3, 2 and negative 4, 3, 0. So notice we're only given 2 points, we aren't given a vector. So since the line intersects both of these points, we can basically choose any point. So let's go ahead and choose R naught as 1, 3, 2, since it doesn't have any negative numbers. So let's just call R naught with its components 1, 3, 2. And so in order to find a vector, remember that these are two different points here. So if we connect these points, we get a line segment. Now what we can do is represent a line segment with a vector. And so once again, the simple formula for that, let's just go ahead and call 1, 3, 2 the first set of points, and negative 4, 3, 0 the second set of points. The simple formula once again is going to be x2 minus x1, comma y2 minus y1, comma z2 minus z1. And so if we represent another vector here, v, let's call it v, is going to equal, so x2 minus x1, so negative 4 minus 1 is negative 5, comma y2 minus y1, 3 minus 3 is 0, and then comma z2 minus z1, so 0 minus 2 gives us a negative 2. So once again, R sub naught is going to contain x sub naught, y sub naught, and z sub naught, and vector v is going to contain a, b, and c. So for the parametric equations, once again, x is going to equal x sub naught, so 1, plus a times t, so it's going to be actually minus 5t. Y is going to equal y sub naught, so 3, plus b times t. Since this is 0, 0 times t is just 0, so we're just going to get 3. And then z is going to equal z sub naught, which is 2. And then plus c times t, which is actually going to be a negative 2t. So those are going to be the parametric equations for the line. So now let's move on to writing the symmetric equations. So once again, symmetric equations are going to be in the form x minus x naught. So x naught in this case is 1 over the a value, and the a value is negative 5, which equals y minus y naught, which is 3, over the b value, and that's 0, which equals c or z minus z naught, which in this case is 2, over the z value, which is negative 2. So now notice that there is a 0 here, but we cannot divide by 0. So we're going to have to put it out separately away from the x and the z. So we're going to go ahead and write x minus 1 over negative 5 equals z minus 2 over negative 2. And then separately we're going to write y equals y naught. So y equals 3. And so those are going to be the symmetric equations. And so for number 2, let's go ahead and find parametric and symmetric equations for the line that goes through the points 0, 1 half 1, and 2, 1, negative 3. Since the 0, 1 half 1 has a fraction, let's just go ahead and make R sub naught represent 2, 1, negative 3. So R sub naught in its component form, once again, is going to be 2, comma 1, comma negative 3. And so let's go ahead and find a vector given 2 points that the line intersects. So let's go ahead and make 0, 1 half 1 the first set of coordinates, and 2, 1, negative 3 the second set of coordinates. So once again, we're going to take x2 minus x1, so 2 minus 0 is 2, comma y2 minus y1, so 1 minus 1 half still gives us 1 half, comma z2 minus z1, so 3 minus a negative 1 gives us negative 4. So that is going to be the vector. So let's go ahead and write the parametric equations. So x is going to equal x sub naught, which is 2. So 2 plus the a value, which is the x component of the vector, so which is 2 times t. So then y is going to equal y sub naught, which is 1, plus b, which is 1 half, times t. And then z is going to equal z sub naught, which is negative 3, plus c, which is the z component of the vector, which is negative 4, times t. So this, instead of plus, is going to be minus 4t. So we have minus 4t. And so those are going to be the parametric equations. So now in order to find the symmetric equations, once again the formula, so we have x minus x naught, so x naught is 2, that's the x component of the R sub naught vector, over the a value, which is the x component of the regular parallel vector, which is 2, equals y minus y sub naught is 1, over the y component of the vector, which is 1 half, which equals z minus z sub naught, and that's negative 3, so that would be plus 3 over the z component, which is -4. Now since this is dividing by 1/2, you could simplify it also to y minus 1 times 2. So that'll give us 2y minus 2. So if I rewrite it, I can rewrite it as x minus 2 over 2, which equals 2y minus 2, which equals z plus 3 over -4. And those are going to be the symmetric equations. So for number 3, let's go ahead and find a vector equation for the line segment from the points 2, -1, 4 to 4, 6, 1. So once again, a vector equation, the formula r is going to equal r sub naught plus t times that parallel vector v. So we need r sub naught and we need a vector v. So since the line segment intersects both of these points, we can choose either one to be r sub naught. Let's just go ahead and pick 2, -1, 4 since that's the first one. So r sub naught is going to equal, in its component form, 2, -1, 4, and in its unit vector form, r sub naught is going to equal 2i minus j plus 4k. So now, let's go ahead and make 2, -1, 4 the first set of coordinates, and 4, 6, 1 the second set of coordinates. If we connect those 2 points together, we get a line segment, and we can represent a line segment with a vector. So once again, vector v, we can represent it by taking x2 minus x1, so 4 minus 2 is 2, comma y2 minus y1, 6 minus a -1 gives us 7, comma z2 minus z1, 1 minus 4 gives us -3. So in unit vector form, v is going to equal 2i plus 7j minus 3k. So let's go ahead and plug it into the vector equation formula. So once again, r is going to equal r sub naught. So that is going to equal 2i minus j plus 4k, and then plus the variable t times vector v in unit vector form, which is 2i plus 7j minus 3k. And so that's the final answer. Now, in order to find an equation of a plane, let's go ahead and draw a plane here. We need a normal vector, so let's call it n. That is going to be perpendicular to the plane, and a point the plane intersects. And so let's go ahead and call that p sub naught. So since this is a plane, we just call it with p. So p sub naught is not going to be a vector like r sub naught, but it's just going to have the coordinates x sub naught, y sub naught, and z sub naught in the third dimension. Now, earlier we talked about the regular equation of a plane, or the standard form, being in the form of xax plus by plus cz equals some constant d. Now, in order to find the equation of a plane given the normal vector and a point of intersection, we have to use the formula a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And so this is called the scalar equation of the plane. And so when we simplify the scalar equation of the plane, we can get it back to the regular form of the plane equation. So let's go ahead and find the equation of the plane for number 1 that goes through the point 6, 3, 2 and perpendicular to the vector -2, 1, and 5. So obviously we can already identify our p naught. So our p sub naught here, the point of intersection, is at 6, 3, 2. Now the normal vector, or the vector that is perpendicular to the plane, let's go ahead and call it v. You can call it n as well for normal. And so that is going to represent its components -2, 1, and 5. So v is going to have its a, b, and c values, while p sub naught is going to have its x sub naught, y sub naught, and z sub naught coordinates. So once again, the formula for the equation of the plane is going to be a times x minus x sub naught plus b times y minus y naught, and then plus c times z minus z naught. That's going to equal 0. So if we go ahead and plug in our variables here, so a is going to be -2, so we have -2 times x minus x sub naught, which is 6, so x minus 6, plus b, which is 1, times y minus y sub naught is 3, and then plus c, which is 5, times z minus z sub naught, and that's going to give us 2. So that's going to equal 0. So if we go ahead and distribute and multiply, we'll get negative 2x plus 12 plus y minus 3 plus 5z minus 10 is going to equal 0. So we're going to get negative 2x plus y and then plus 5z. And that's going to equal, now 12 minus 3 gives us 9, and 9 minus 10 gives us a negative 1. So if we add over negative 1 to the other side, we'll get a positive 1. So that is going to be the final equation of the plane. So for number 2, let's find the equation of the plane that goes through the point 1, negative 1, 1. So our P0, our point of intersection here, that the point the plane intersects is going to be 1, negative 1, and 1. And then it has a normal vector of I plus j minus k. So if we write the normal vector I plus j minus k, so let's say v, the normal vector is going to be that. Now if we write that in standard component form, we can also write it as 1, 1, negative 1. So that's going to be our a, b, and c values. And then we're going to have our x naught, y naught, and z naught coordinates. So once again, the formula is going to be a, so that's going to be 1 times x minus x naught is going to be 1, plus b, which is 1, and once again, times y minus y naught. So if y naught's negative 1, then we basically add 1, and then plus c, which is negative 1, times z minus z naught, which is 1. And that's going to equal 0. So we're going to get x minus 1 plus y plus 1, and then minus z plus 1 is going to equal 0. So x plus y minus z is going to equal, now negative 1 plus 1 will cancel. We have another 1 here, and if we subtract that to the other side, we'll get negative 1. So x plus y minus z equals negative 1 is going to be the final equation of the plane. So now for number 3, let's find the equation of the plane, given that the plane goes through the points 0, 1, 1, 1, 0, 1, and 1, 1, 0. So notice that we're not given a normal vector or a perpendicular vector. Instead, we're given 3 points. Now, since the plane goes through all 3 points, we can pick anything to be our P naught. Since 0, 1, 1 is the first one, let's just go ahead and pick that one. So P naught, let's represent as 0, 1, 1. Well, what can we do with these 3 points? So I'm going to go ahead and label point A as 0, 1, 1, point B as 1, 0, 1. Let's just call point C then 1, 1, 0. Now with these 3 points, I can create 2 different line segments. Let's create AB, line AB, and also line AC. And remember, we can represent line segments with vectors. So then we'll label it vector AB and vector AC. So let's go ahead. So vector AB is going to be calculated by taking x2 minus x1, so 1 minus 0, which is 1, comma y2 minus y1, 0 minus 1 is negative 1, and then comma z2 minus z1, so 1 minus 1 gives us 0. And so vector AC can be calculated with, once again, x2 minus x1, so 1 minus 0 gives us 1, y2 minus y1, 1 minus 1 is 0, and then comma z2 minus z1, which gives us negative 1. Now I'm going to go ahead and rename vector AB as just vector A, and rename vector AC as just vector B, just for sake of simplicity. Now, what we have here are 2 vectors that are within the same plane, but what we need is a normal vector that is perpendicular to the same plane, not parallel to the plane. So what we can do, remember that cross product of A and B, so 2 vectors A and B, the cross product yields another vector, but this time the vector is going to be perpendicular to both vectors A and B. So if we take the cross product of both of these, then we can find a normal vector or a perpendicular vector to the plane. So remember, when we take the cross product, we're going to create a matrix here. So on the top row we have I, J, and K. Since A is being multiplied first, we'll put its components on the second row. So A's components are 1, negative 1, and 0. And B's components are 1, 0, and negative 1. And let's go ahead and put it in determinant notation. So once again, we start with the top leftmost value, so I. So we're going to cross out the row and column I is in, and then write what's left inside of a smaller matrix. So what's left is negative 1, 0, and 0, negative 1. The next term is going to be subtracted. The next term is J. So we have j times, if we cross out its row and column, we have 1, 0, and 1, negative 1 that's left. And the final term is going to be positive, so k, we cross out its row and column, and what we have left is 1, negative 1, and 1, 0. So now we can go ahead and cross multiply. So when we cross multiply, we'll get I times, now negative 1 times negative 1 is 1, minus 0 times 0, which gives us 0, and then minus j times 1 times negative 1 is negative 1, minus 1 times 0, which is 0, and then plus k times 1 times 0, which is 0, minus 1 times negative 1, which is negative 1. So plus 1. So 1 minus 0 is 1. 1 times I is I. And then minus negative 1 minus 0 is negative 1. So negative 1 times j is negative j. So now it's going to become a positive j. So minus a negative is positive. And plus 1 times k, which is k. So that is going to be the normal vector that is perpendicular to the plane. And so if I write that in component form, we can write it as 1, 1, 1. So now, given a point of intersection and a normal vector, we can go ahead and write the equation of a plane. So once again, the vector is going to be in its a, b, and c components, and then p naught is going to have its x naught, y naught, and 0, or z naught components as well. So we're going to take a, which is 1, times x minus x naught, which is 0, plus b, which is 1, times y minus y naught, which is 1, and then plus c, which is also 1, times z minus z naught, which is 1. And that's going to equal 0. Now if we simplify, we'll get x plus y minus 1 plus z minus 1 equals 0. So negative 1 minus 1 is a negative 2, and if we add to the other side, we'll get a positive 2. So the final equation of the plane is x plus y plus z equals 2. So now let's say we're given a set of parametric equations that represent a line, and we're given the equation of a plane, and we're trying to find the point at which the line intersects the plane. So for number 1, we have x equals 3 minus t, y equals 2 plus t, and z equals 5t, and the equation of the plane is x minus y plus 2z equals 9. So given this information, all we have to do to find the point of intersection is to plug in each of these parametric equations into the equation of the plane. So if x is equal to 3 minus t, we'll plug that in for x. If y is 2 plus t, we'll plug that in for y, and then we'll plug in 5t for z. And so what we do is we solve for t, and then we'll go from there. So let's start by plugging in the parametric equation to the given plane. So for x, we have 3 minus t, and then minus y. Now y is going to equal 2 plus t, and then plus 2 times z, which is equal to 5t. And that will equal 9. So 3 minus t, we have that, and then minus 2 minus t, and then plus 2 times 5t, which is 10t, is going to equal 9. So then if I go ahead and subtract 3 minus 2, we get 1. So we get 1 minus, now t, negative t minus t will be negative 2t. Negative 2t plus 10t will give us positive 8t. That's going to give us equal to 9. So then 8t is going to be equal to 9 minus 1, which is 8. So then t is going to equal 1. So now that we know t is equal to 1, we can go ahead and plug in t, or 1, for each of the t values of the parametric equations. And then we'll get each x coordinate, we'll get the y coordinate, and then we'll get the z coordinate as well. So if we go ahead and plug in 1 for t in the x equation, we'll get x equals 3 minus 1, which is 2. We plug in 1 in the y equation, we'll get y equals 2 times, or 2 plus 1, which is 3. And then in the z equation, we'll get z equals 5 times 1, which is 5. So the coordinates for the point of intersection is going to be at 2, 3, 5. So now let's say we have to determine whether the planes are perpendicular, parallel, or neither in relationship to each other, and if neither, find the angle between them. So for number 1, we have x plus 4y minus 3z equals 1, and the other plane equation is negative 3x plus 6y plus 7z equals 0. So what we have to do here is find normal vectors for both of these planes, or just one normal vector for each of them that represents that plane, and then we can find whether those two vectors are perpendicular, parallel, or neither. So let's go ahead and find the normal vector for the first plane equation here, x plus 4y minus 3z equals 1. So once again, planes are in the equation, or in the format, where we have xax plus by plus c times z equals some constant d. So the normal vector, once again, is just going to be in the format a, b, c. Now we can call the normal vector n or v, it doesn't matter. So in this case, let's just call it n. And that's going to have the components. The 1 is in front of the x, so we have 1, 4, and negative 3. So that is going to be the components of the normal vector for x plus 4y minus 3z equals 1. Now for negative 3x plus 6y plus 7z equals 0, the normal vector for that one is going to be negative 3, because that's in front of the x, positive 6, and positive 7. Just go ahead and call this one, the first vector, let's call that a, and then for the second vector, let's call that b. Vector b. Now remember, if we take the dot product of a and b, and we get 0, that means those two vectors, or in this case those two planes, are going to be perpendicular or orthogonal to each other. And if they're not perpendicular, then we have to use the formula of cosine of theta equals the dot product of a times b over the magnitude of a times the magnitude of b, in order to get us to find that angle in between those two vectors, or those two planes. So then we can see either if it's parallel or neither. So let's go ahead and take the dot product of vectors a and b. So for the dot product, once again, we're going to multiply the same components. So the x components go first. So 1 times negative 3 is negative 3. So then we add the y components being multiplied to each other. So 4 times 6 gives us 24, and then plus the z components. So negative 3 times 7 is a negative 21. So 24 minus 21 gives us 3, and negative 3 plus 3 gives us 0. So if it's 0, we know that the relationship between the planes, or the angle, is going to be perpendicular or orthogonal. So for number 2, we have x plus y plus z equals 1, and x minus y plus z equals 1. So let's go ahead and find the normal vectors. So let's just call this, or let's just call the normal vector that represents the first plane, vector a. And so that's going to be just 1, simply 1, 1, 1, because those are the coefficients in front of x, y, and z. And let's call the second one vector b, that represents x minus y plus z. And so that's going to have the components 1, negative 1, 1. So let's go ahead and first take the dot product here. So dot product of a times b is going to equal 1 times 1. It's going to give us 1, plus 1 times negative 1 is negative 1, and then plus, once again, 1 times 1, which gives us 1. So that's just going to give us a value of 1. So that does not equal 0, so we know the relationship, or the angle, is not perpendicular. So we have to take that extra step and use the formula cosine of theta equals the dot product of a times b over the magnitude of a times the magnitude of b to actually find out what that angle is. So the dot product of a times b, we already got 1, so that's going to be on the numerator. Let's go ahead and find the magnitude of a. So once again, the magnitude for vector a is going to be the square root of the x component squared plus the y component squared plus the z component squared. So we go ahead and take the square root of 1 squared plus 1 squared plus 1 squared, and so we'll get the square root of 3. Now realize that in order to find the magnitude of b, it's going to be the exact same answer as well. The square root of 1 squared, which is 1, plus negative 1 squared, which is 1, and then plus 1 squared, 1. So we'll also get the square root of 3. So that's going to be equal to the magnitude of a. The square root of 3 is also going to be equal to the magnitude of b. So we get 1 over the magnitude of a, which is the square root of 3, times the magnitude of b, which is also the square root of 3. So then we'll get 1 over the square root of 3 times the square root of 3, which is 3. So if cosine of theta is equal to 1 over 3, in order to find theta over that angle, we have to arc cosine or inverse cosine both sides. So theta is going to equal to the inverse cosine of 1 over 3. So when I use my calculator, it should be around 70.5 degrees, the angle in between the two planes. And so the answer is neither, because it's not, the relationship or the angle in between the two planes is not parallel nor perpendicular, but it is neither, and the exact angle is, or the approximate angle is around 70.5 degrees. So now let's just say we're trying to find the distance from a point to a given plane. So remember the formula for a plane here is going to be ax plus by plus c times equals some constant d. Now if you go ahead and subtract d to the left side, we'll get ax plus by plus cz minus d equals 0. And that's the form we want it in to calculate using the distance formula. So the distance formula here is going to be equal to a times x1 plus b times y1 plus c times z1 minus d, the absolute value of it, all over the square root of a squared plus b squared plus c squared. Now x1, y1, and z1 is just going to be that given point that we're trying to find the distance of from the point to the plane. And then a, b, c, and d are going to be those, well, a, b, and c are going to be the coefficients of the plane, obviously, the given equation of the plane. D is going to be that constant, and so we can plug all those numbers in and find the distance. So for number 1, we're trying to find the distance from the point 285 to the given plane, x minus 2y minus 2z equals 1. So the first thing we have to do is label out our variables here. So 285 is going to be our given point. That's going to be our x1, y1, and z1. And so since our 1 is going to be that d value, we have to subtract over 1 to the left side, so we can get it in the form of ax plus by plus cz plus d equals 0. So we get it in the form of x minus 2y minus 2z minus 1 equals 0. So now we can go ahead and plug all these numbers into the distance formula. So the distance formula, once again, is going to be a times x1 plus b times y1 plus c times z1 minus d, and the absolute value of it, over the square root of a squared plus b squared plus c squared. So plugging in all the numbers here, the distance is going to equal to the absolute value. Now a is going to be that coefficient in front of the x. So that's just going to be 1 times x1, which is the x coordinate of the point. So that's 2. Then we have plus b. b is going to be the coefficient in front of the y. So that's negative 2 times y1, which is 8. And then plus c, which is also negative 2, times z1, and that's 5. And then we have plus d. d is going to be negative 1. We have minus 1. Absolute value close all over the square root. Now a squared is going to be 1, so 1 squared is 1, plus b squared, so that's going to be 4, and then plus c squared, which is also 4. So we're going to end up getting the absolute value of 2 minus 2 times 8, so minus 16, minus 2 times 5, which is 10, and then minus 1, all over the square root of 9. So the square root of 9 is obviously 3. We get 3 on the bottom, and then 16 minus 10 is negative 26, negative 27. So then 2 minus 27 will get us a negative 25. Since we have the absolute value, we can evaluate it, and so our final answer is going to be 25 over 3 as the distance from the given point to the given plane. So now for number 2, let's find the distance between the given parallel planes. So this time we're not given a coordinate in a plane, we're given 2 planes. So for z equals x plus 2y plus 1, and the other plane is 3x plus 6y minus 3z equals 4. Now when we're given 2 planes, what we can do is choose a point that lies in one of the planes, and we find the distance from that point to the other plane. So let's go ahead and take this equation here, z equals x plus 2y plus 1. Let's go ahead and find a point in this plane. What we can do is let's plug in 0 for both y and z. So what we get here is 0 equals x plus 1, which means x equals negative 1. So that tells us that a point on the plane is going to have the x value of negative 1 a y value of 0 and a z value of 0, since we plugged in 0 for both z and y. So now we can go ahead and find the distance from this point to the other plane. So -1 is going to be our x1, 0 is the y1, and z1 is also the 0. And so let's go ahead and use the distance formula here. So the distance formula is going to be the absolute value of a. Now the a value is going to be the coefficient in front of the x in the equation of the plane, so 3 times x1, so that's -1, and then plus b, which is going to be 6 because that's in front of the y, times y1, 0, and then plus c, -3. So that's going to be, instead of plus, we're going to have a minus here. Minus 3 times z1, that's going to be 0, and then plus d. And so let's go ahead and subtract over the 4. So then we get 3x plus 6y minus 3z minus 4 equals 0. So now that it's in the form, we can go ahead and identify our d value as a -4. We take the close the absolute value, and now over the square root of a squared, so that's going to be 3 squared root is 9, plus b squared, that's 36, and then plus c squared, -3 squared is 9. So on the top, on the numerator, we'll get the absolute value of -3 plus 0, and then minus 0, minus 4. And then on the denominator, we'll get the square root of 36 plus 9 plus 9, which is 18. So 36 plus 18 gives us 54. Now, 9 times 6 is 54, so we can simplify the square root of 54 into 3 times the square root of 6. And on the numerator, we'll get -3 minus 4, -7, and the absolute value is 7. So we get 7 over 3 times the square root of 6, multiplied by the square root of 6 over square root of 6. So then we'll get 7 times the square root of 6 over 3 times 6, which is 18, as our final answer for the distance.